Hi students, how are you doing? I think you all are fine. Everything is fine, isn't it? In physics, yesterday I started the fourth unit, work, energy and power. There, work. Define work or what is work? Work is said to be done by the force when the force applied on a body displaces it. Work is defined on the basis of force and displacement. Then I have explained about the expression for work done, that is W is equal to F dot dr or F dr cos theta. Then what is the unit of work? That is Newton meter or joule, and dimensional formula is ml square t raised to minus 2. Then we have seen the special cases for zero work done. That is when F dr equal to 0, the work done is 0. When theta equal to 90 degree, the work done is 0. Then I discussed about the negative work done. Also, we have seen the different angles. What is the nature of the work? For theta equal to 0, the work is said to be positive. For theta equal to 90 degree, the work is 0. For theta equal to 180 degree, the work is said to be negative. Then work done by a constant force and work done by a variable force also we have discussed. Alright. Today I am going to teach energy. To do work, energy is required. Isn't it? To do work, energy is required. So what is meant by energy? Energy is the ability to do work or define energy. Energy is defined as the capacity to do work. Capacity to do work. Actually, work and energy are equivalents and have the same dimension. That is, work done is the manifestation of energy. Work done is the manifestation of energy, or work is equal to energy, or energy is equal to work. So, work and energy has same unit and same dimensional formula. That is, the unit, SI unit of energy is equal to Newton meter or joule. Isn't it? For work also the same unit, Newton meter or joule. And the dimensional formula, what is the dimensional formula for work? That is ml square t raised to minus 2. For energy also we can say ml square t raised to minus 2 is the dimensional formula for energy. Understand? That is work done is the manifestation of energy. In the lower classes, you have heard many types of energy, such as thermal energy, nuclear energy, electric energy, mechanical energy, and so on. So in this chapter, we are dealing mainly with the mechanical energy. In this energy topic, we have to understand one important concept that is called law of conservation of energy. This also you have learnt in the 10th standard. State law of conservation of energy. Energy can neither be created nor be destroyed, but one form of energy can be transformed to another form of energy, isn't it? So the concept is total energy remains the same in any process. The total energy of the system remains constant, or we can say total energy remains the same in any process irrespective of whatever the internal energy may takes place. Okay? Mechanical energy. What is mechanical energy? The energy of an object due to its motion or its position. Isn't it? The energy of an object due to its motion or its position. That is the sum of the kinetic energy and potential energy. We can call it as the mechanical energy. So mechanical energy is classified into two. That is kinetic energy and potential energy. Kinetic energy and potential energy. So what is kinetic energy? What is potential energy? Kinetic energy is the energy possessed by the body due to its motion. Kinetic energy is the energy possessed by the body due to its motion. Potential energy, energy possessed by the body by the virtue of its position. Potential energy, the energy possessed by the body by virtue of its position. Okay. Today we can discuss about kinetic energy. All moving objects have kinetic energy because kinetic energy is the energy possessed by the body by virtue of its motion. So all the moving objects have kinetic energy. A body that is in motion has the ability to do work. Okay. You have learned the expression for kinetic energy in the lower classes, such as kinetic energy is equal to half mv square. Half mv square. So here the amount of work done, that is the kinetic energy. Energy is equal to work done. Work done is equal to energy. So I can say the amount of work done of a moving body depends upon the mass of the body and its velocity, where m is known as the mass of the body, v is known as the velocity of the body. This is the expression for kinetic energy. So kinetic energy depends upon mass and velocity. Half mv square. A body which is not in motion does not have kinetic energy. Understand? There is a demonstration of kinetic energy given in your book. That is hammer, nail and wood. When the hammer kept at rest on a nail, okay, just we are keeping the hammer on the nail, this nail would not push into the wood. Isn't it? When the hammer kept at rest on nail, does not push the nail into the wood. But when we are striking the hammer, this we are doing some work. Okay, when we are striking the hammer with the nail, what happens? This nail draws into the wood. Nail draws into the wood. Understand? So here the amount of work done by the moving body depends upon the mass and velocity of the body. So here kinetic energy is the measured by the amount of work that the body can perform before it comes to rest. Kinetic energy is measured by the amount of work that the body can perform before it comes to rest. Okay, students, give some examples for kinetic energy in everyday life. A bicycle in motion possesses kinetic energy. Running water has kinetic energy. Moving car has kinetic energy. Windmill. Windmill form one of the good example of application of kinetic energy. Bullet from a gun has the kinetic energy, etc. and so on. Isn't it? So I hope you understand about the kinetic energy. Let's see an important question. Work-kinetic energy theorem. Work-kinetic energy theorem. What the theorem says? That is, the work done by the force on the body changes the kinetic energy of the body. The work done by the force on the body changes the kinetic energy of the body. This is called work-kinetic energy theorem. That is, work and energy are equivalents, isn't it? So it is true for the kinetic energy also. So the work done by the force on the body changes the kinetic energy of the body. This is called work-kinetic energy theorem. So I can write in the expression W is equal to delta K. W is equal to delta K. We are going to prove this theorem. Let us consider a body of mass m. Mass m which is at rest on a frictionless surface. Okay. Now, a force is applied on this body which moves the body as a displacement S. So, displacement is S. So, what is the work done by this force? Let us write work done by this constant force as W is equal to force into displacement. So, F into S. What is the work done formula? Force into displacement. So, I can write W is equal to F into S. Consider this as equation 1. Already we know the formula for force. What is force according to Newton's second law? F is equal to m into A. Mass into acceleration, where A is known as the acceleration. Consider this as equation 2. Now, we are going to find the value of acceleration and substitute in this equation. Then, finding the value of work done. To find acceleration, I am taking the third equation of motion. What is the third equation of motion? That is v square equal to u square plus 2as. V square equal to u square plus 2as. From this, find the value of acceleration. That is v square minus u square is equal to 2 into a into s. From this, a is equal to what? V square minus u square by 2s. A is equal to v square minus u square by 2s. Now, substitute the value of A in equation 2. Substitute the value of A in equation 2. What is equation 2? F equal to m into A. So, F equal to m into v square minus u square by 2s. Isn't it? F is equal to m into A. A is v square minus u square by 2s. Okay. Now, consider this as equation 3. Substitute equation 3 in equation 1. What is equation 1? W is equal to Fs. So, W is equal to Fs. Instead of F, we can substitute m into v square minus u square by 2s. Isn't it? V square minus u square by 2s into s. This is F, this is S. So, how can we write this? mv square by 2s into s minus mu square by 2s into s. mv square by 2s into s minus mu square by 2s into s. So, here SS get cancelled. W is equal to half mv square minus, here also SS get cancelled, half into mu square. This is equation number 4. So, what is the expression? W is equal to half mv square minus half mu square. What is half mv square? Nothing but the kinetic energy. W, otherwise kinetic energy is equal to half mv square. So, how can we write this equation? This is half mv square minus half mu square. V is the final velocity, u is the initial velocity. So, I can write this as the change in kinetic energy. Change in kinetic energy. That is delta Ke. This delta represents the change. Change in kinetic energy is equal to half mv square minus half mu square. We can say final kinetic energy minus initial kinetic energy. Final kinetic energy minus initial kinetic energy. So, comparing these two equations, I can write W is equal to delta into Ke. W is equal to delta into Ke. Hence the theorem proved. What is that? The right hand side of the equation is change in kinetic energy. Left hand side is work done. So what the theorem states? The work done by the force on the body changes the kinetic energy of the body. This is called a work-kinetic energy theorem. Very important question. For this question, first we have to write the statement. This is the statement. Then we have to write the expression. That is, first work done formula, force in displacement. Then force formula, mass into acceleration. Acceleration we have to find it from the third equation of motion. A is equal to v square minus u square by 2s. Then substitute this value here and find the value of work done. That is F equal to m into v square minus u square by 2s. When you are substituting, the s value get cancelled. So we got W is equal to half mv square minus half mu square. That is kinetic energy is equal to half mv square. So I can write W is equal to delta Ke. This is called the work kinetic energy theorem. Here we can discuss some special cases. Okay. First point, if the work done by the force is positive, if the work done is positive, the kinetic energy increases. The kinetic energy increases. Second point, if the work done by the force is negative, if work done is negative, then its kinetic energy gets decreases. Kinetic energy gets decreased. From the formula we can understand. If you are finding the difference, if it is positive value, we can understand that the kinetic energy is increases. If you are finding the difference, we are getting the negative value means we can understand this kinetic energy decreases. So negative value means work done is negative, so kinetic energy decreases. Positive value means work done is positive, so kinetic energy increases. Third point, if there is no work done, if there is no work done by the force on the body, no work done, if work done is equal to 0, what does it mean? There is no change in kinetic energy. Kinetic energy, there is no change. That means the body has moved at constant speed with the provided its mass remains constant. Okay. So this is the special case. When you are writing this question, you have to include this special case also. I think you have understand this question. Prepare well this question. Write and practice in your notebook. Okay. Let's see the next topic. That is relation between momentum and kinetic energy. Relation between momentum and kinetic energy. Momentum. What is that? P. P is equal to m into v. Mass into acceleration. Kinetic energy half mv. So what is the relation between these two? Okay. So consider an object of mass m moving with velocity v. So what is the linear momentum? The linear momentum of the object is p vector is equal to m into v vector. And what is the kinetic energy? The body is moving with velocity means it possesses kinetic energy. So what is kinetic energy? Kinetic energy is equal to half mv square. I am rewriting this kinetic energy as Ke equal to half mv square is equal to half into m into v into v. V square can be written as v into v. Consider this as equation 1. Or this is equation 1, this is equation 2, this is equation 3. Okay. Here multiply and divided by m on this equation 3. That is equation 3 into m divided by m. That is kinetic energy is equal to half into m into m. So m square into v divided by m. Multiplying by m and divided by m. Understand? And this equation again can be written as half into m square. I can split and write mv into mv. Okay. So mv into mv. It means m square v square. M square v square divided by m. So what is mv? Yes. mv is equal to p, or p is equal to mv. So half into p into p. P into p divided by m. Since p is equal to mv. Okay. So answer is p square by 2m. Kinetic energy is equal to what? P square by 2m. This is equation number 4. Where p is the magnitude of momentum. And this p value, how can we write? That is p square equal to 2m into kinetic energy. Or else p is equal to, the magnitude means we can write like this, p is equal to, or p is equal to root of 2m into kinetic energy. Root of 2m into kinetic energy. This is the relation between momentum and kinetic energy. P is equal to root of 2m into ke, kinetic energy. So listen. Consider an object of mass m moving with velocity v. It possesses the linear momentum p is equal to mv, and the kinetic energy k is equal to half mv square. So I can rewrite the half mv square as half mv into v. Then multiplying both numerator and denominator by m. So k is equal to half into m square vv divided by m. This I can rearrange as mv into mv. That is mv into mv by m, half into p by m, because p is equal to mv. So kinetic energy is equal to p square by 2m, or p square equal to 2m into kinetic energy. So p is equal to root of 2m into kinetic energy. Here you have to notice one point. If kinetic energy and the mass are given, we can calculate the value of momentum. Only the magnitude of momentum, not the direction of momentum. Momentum is a vector quantity, isn't it? So when the mass and kinetic energy is given, we can calculate only the magnitude of momentum, because kinetic energy and mass are scalars. Understand? Let's see the example 4.7 from your book. Two objects of masses 2 kg and 4 kg are moving with the same momentum of 20 kg per second. Two objects 2 kg and 4 kg moving with the same momentum 20 kg per second. A. Will they have same kinetic energy? B. Will they have same speed? Same momentum, whether they have the same kinetic energy and whether they have the same speed. Let's analyze this question. Solution. That is, two mass are given. That is, consider m1 equal to 2 kg, m2 is equal to 4 kg, and the momentum is p is equal to 20 kg meter second raised to minus 1. First, find the kinetic energy of the 2 kg mass. Okay, so kinetic energy 1 is equal to half m1 v square. That is, kinetic energy, another formula is p square by 2m, because here the velocity is not given, momentum is given. So I can have the formula p square by 2m. That is, what is p square? 20 kg meter second raised to minus 1. So 20 into 20 divided by 2 into, what is the mass? First object 2 kg. What is the answer? 20 into 20, 400 divided by 2 into 2, 4. So what is the answer? 100 joule for the first mass. For the second mass, that is for 4 kg, the kinetic energy Ke2 equal to P square by 2m2. That is P is 20. 20 into 20 divided by 2 into what is mass? Second mass 4 kilogram. What is the answer? 400 divided by 8. That is 50, isn't it? 50 joule. So kinetic energy 1 is what? 100 joule. Kinetic energy 2 is 50 joule. So what is the answer? Kinetic energy 1 is not equal to kinetic energy 2. Even though the two objects have same momentum, the kinetic energies of the masses is not same. Isn't it? So kinetic energy of the heavier object has lesser kinetic energy than the smaller mass. That is, for 2 kilogram mass we are getting 100 joule, but for 4 kilogram of mass we are getting 50 joule. Isn't it? So kinetic energy is inversely proportional to the mass. Kinetic energy is inversely proportional to the mass for a given momentum. For a given momentum. Understand carefully. We know the general formula for kinetic energy is half mv square. Accordingly, we can say kinetic energy and mass are directly proportional. But for a given momentum, that is kinetic energy is p square by 2m. So kinetic energy is inversely proportional to mass. Inversely proportional to mass. So I can say heavier mass has lesser kinetic energy. Okay. Lesser mass has higher kinetic energy. This is the first question answer. The kinetic energies are not same even though the momentum is same. What is the second question? Will they have same speed? Will they have same speed? As the momentum formula is P equal to m into V, the mass differs, isn't it? Mass differs. 2 kilogram and mass 4 kilograms are given. The two objects will not have same speed. Momentum is the product of mass and velocity. So, the two objects will not have the same speed. Got it? I think you have understood this problem and the concept. In your book, page 173, table 4.2, SI equivalent of other units of energy is given. SI equivalent of other units of energy. Unit equivalent in joule. Okay. So these are the other units of energy. That is 1 erg. That is a CGS unit, Gaussian system of unit. What is 1 energy? That is equal to 10 power minus 7 joule. 10 power minus 7 joule. Second, 1 electron volt. This is also another form of unit of energy. 1 electron volt, EV. It has the value 1.6 in 10 power minus 19 joule. 1.6 in 10 power minus 19 joule. 1 calorie. 1 calorie, that is calorie, that is equal to 4.186 joule. 4.186 joule. 1 kilowatt hour. 1 kilowatt hour kWh, that is equal to 3.6 in 10 power 6 joule. So these values you have to learn. For solving problems it will be useful. Okay friends, today we have discussed about energy. Mainly the kinetic energy. Kinetic energy is one of the type of mechanical energy. Kinetic energy is the energy possessed by the body by virtue of its motion. Then the dimensional formula and the unit of work and energies are equal. Then I have explained about the work kinetic energy theorem and special cases. Learn this question. Also we have seen the relation between kinetic energy and momentum. Study these questions, students. Thank you.